Hello class, we're about to start lesson 1-8 portion control. Our learning objectives is to describe what apportionment is and why it's used, to compute standard divisors and quotas, and to apportion items using a variety of methods. Okay, we go down here to the bottom of the page. It says the most common example of apportionment, and as we'll see where the study came from in the first place, is the United States Congress. There are 100 senators in 50 states, 2 senators per state, easy. But in the House of Representatives, the number of representatives is based on the population of the state. There are 435 seats in the House, and they're divided according to population. For example, Florida has 25 seats. Pennsylvania has 19, and Rhode Island has just 2. So why can't we just divide 435 by the population to find out how many representatives per person, then multiply by the state's population? Because it's against the law to divide politicians into pieces. Almost every state would be entitled to a non-integer number of seats, which won't work. That's where apportionment comes in. Apportionment is the process of fairly assigning identical indivisible objects among individuals entitled to shares that may be unequal. We just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. This number is known as the standard divisor, and it plays a really important role in apportionment. So we'll highlight the formula next, but don't think about memorizing it. Think about what it means, and you'll have a much better chance of understanding this lesson. Throughout this lesson, we'll refer to the objects being assigned as seats, like seats in Congress. The individuals they're allocated to will be called districts. Now we move on to the next page. And at the top here, we have the standard divisor formula, where it says the standard divisor is the total population divided by the number of seats. Now, here's the apportionment problem we'll be working on in this lesson. A large city has 20 seats to be allocated proportionally among 5 districts according to the population of each district. The populations of the districts in thousands are shown in the table. Explain why it wouldn't be fair to just assign 4 representatives to each district. And the reason is their populations are vastly different. For example, District 5 versus District 2. Okay, number 2. It says find the standard divisor for this apportionment and briefly describe what it means. Okay, so the standard divisor, going to abbreviate with SD, we would take the total population. Our total population is technically 240,000 because this is in thousands. So we have TP, which is total population divided by number of seats. So our total population was 240,000 divided by the 20 seats. And that will give us 12,000. Okay, so now it says number 3. Well, it says for us to describe what it means. So we have to put there should be 1 seat for every 12,000 people. Okay, now number 3. It says, notice that District 2 has exactly 1/3 of the population. It would seem perfectly reasonable then for that district to get 1/3 of the seats. Why won't District 2 get exactly 1/3 of the seats? And I will show you this here. There are 20 seats. 1/3 of that is the same as just dividing 20 by 3. When you divide 20 by 3, that will give you 6.6, well, repeating sixes. That's what that would give you. So it would not give you an integer. And so you could say it does not divide evenly. That's why it does not divide evenly. That's why you would not get exactly 1/3 of the seats. Now we come here to the next page, page 97. It says, while we've seen that you can assign seats simply based on what percentage of the total population a given district has, that percentage still plays an important role in apportionment. If we divide the population of a given district by the standard divisor, something interesting happens. Now, we have the population of the district divided by the standard divisor. The standard divisor was rewritten to what it was on the previous page. The standard divisor is the total population over number of seats, and we changed standard divisor to total population over number of seats. So if we rewrite this mathematically, I'm going to put PD for the population of the district divided by the total population, which is TP, over the number of seats. Now, this is what this actually means, and we're going to get to why this is significant pretty soon. Okay, number 4. It says, given the fact that dividing by a fraction is the same as multiplying by its reciprocal, fill in the blanks to rewrite the division above as a multiplication. So this is where this comes into play. So I rewrote this as this here, and then we would take this here and change it to multiplication. So population of district, the division becomes multiplication, and we know we take the reciprocal, so it'd be number of seats divided by the total population. Now, we can rearrange the multiplication a bit using properties of multiplying fractions. So, basically what this is saying is we could take the population of the district over the total population times the number of seats. So what we did here, we shifted the denominators. So if we put this over 1 here, we will be able to multiply this out. But we will get to that in the next problem. It says here, number 5, perform the calculation in the formula above. For District 3 in our example problem. Then write a description of what the result of the calculation tells you. Okay, so we will add a population of the district divided by the total population times the number of seats. So the population of the district is 41,000. The total population is 240,000. Now remember, we're not using this up here. We're going back to the previous page on 96 and using these values here. And remember, the population is in thousands. Okay, so now, took the population of the district, which was 41,000, the total population, 240,000, times the number of seats. The number of seats is 20, and we can put that over 1. So when we multiply this, this will give us 820,000 divided by 240,000. And when you put that in your calculator, let's pull up Desmos. Pull that into the calculator. We had 820,000 divided by 240,000. And that will give us approximately, if we round to 2 decimal places, 3.42. Let me minimize that. It'll be approximately 3.42. So what this is saying is that this district, which is they, should get 3.42 seats if this was possible. Okay, now we go here to our next page. And it says the formula we built, which is the percentage of the total population that lives in a given district multiplied by the total number of seats, is the theoretical number of seats that each district would get if it were possible to hand out fractional portions of seats. We call this number the standard quota. So the standard quota is equal to the population of the district divided by the standard divisor. It describes the number of seats that each district would be assigned if it made sense to assign fractional portions of seats. Okay, so with that being said, it says find the standard quota for each district in the city described on page 96. Now, if you look here back on page 96 at the districts, District 1 is 32,000. So what I'm going to do, I'm going to just write the district number, and I'm going to write their population of the district. And I'm just going to do that for each district here. District 2 was 80,000. District 3 is 41,000. District 4 is 67,000. And District 5 is 20,000. Okay, now, they tell us that with this problem here, we have to divide by the standard divisor. We already found the standard divisor. When we go back here to problem number 2 on page 96, our standard divisor was 12,000. So we divide each one of these by 12,000. And we're going to do like we did with District 3. We're going to round to 3 decimal places for each one. 2 decimal places. Okay, so now, let me get this calculator here. So we'll start. We have 32,000 divided by 12,000. Then we would do 80,000 divided by 12,000. We already did District 3, but I'll just redo it. 41,000 divided by 12,000. District 4, 67,000 divided by 12,000. And then District 5 was 20,000 divided by 12,000. All right, now we need to write down and we need to round. So with District 1, it'll be 2.67. District 2, it'll be 6.67. District 3 is 3.42. District 4 is 5.58. And then finally, District 5 will be 1.67. So now we have all of our standard quotas for each one. Now it says, now that we know how to almost find the number of seats that should go to each district, aside from the pesky issue of fractional parts, the rest of the study of apportionment is about deciding if each district number of seats should come from rounding its standard quota up to the next bigger whole number or down to the next smaller number. Seriously, that's pretty much it. A logical place to start is by simply using familiar rounding rules. So let's give that a try. All right. So we move on here to the next page. Now we look here at problem number 7. Okay, problem number 7, it says round each standard quota you calculated in question 6 to the nearest whole number. Then add the results and explain why that won't work as the number of seats assigned to each district. Okay, so if we go back here, and I do not like flipping back and forth, but if you notice here, this would round to 3, District 2 would round to 7, District 3 would be 3, District 4 would be 6, and District 5 would be 2. So we would add all of those numbers. We add 3, 7, 3, 6, and 2. So that would give us 21. But the problem is we only have 20 seats. So now we ran into a problem. So now, of course, in math, we like to solve problems. So let's go down here. Question 7 shows that simply rounding each standard quotient to the nearest whole number isn't a reliable method of apportionment. This realization dates back to at least 1790, when both Alexander Hamilton, the first Secretary of the Treasury, and Thomas Jefferson, hopefully you know who he was, suggested methods for apportioning congressional seats after our nation's first official census. The methods of apportionments that we'll study are all based on first calculating the standard quota, then deciding whether to round up or down. For any district, the lower quota is the result of rounding the standard quota down to the nearest lower whole number. The upper quota is the result of rounding up to the next larger whole number. Okay, number 8. Our standard quotas. We had that on the previous page. District 1 is 2.67, and then we have all of the rest. So we need to put those in for our standard quota. So we add 2.67, 6.67, 3.42, 5.58, and 1.67. Okay, now, I know with the explanation, they gave you a good sound mathematical explanation, but I want to give you an explanation that will be a little bit more practical. When they ask you for the lower quota, instead of saying rounding up and down and everything, just look at it like this. The lower quota is always the digit in front of the decimal of your standard quota. So the digit here would be 2, this would be 6, this would be 3, this would be 5, and this would be 1. So your lower quota is always the numbers in front of the decimal. Now, once you find the lower quota, the upper quota is easy. All you got to do is just add 1 to your lower quota. So this would be 3, 7, 4, 6, and 2. So again, just to recap this, to get the lower quota, you just take the number in front of the decimal. To get the upper quota, just add 1 to the lower quota, and you have the upper and lower quota. All right, now we move on here to page 100. Now it says, now we're all set up for the group portion of the lesson, where we'll study several apportionment methods. Make sure you think about the key idea in the remainder of this lesson. All of our apportionment methods are based on finding the standard quota, then deciding whether to round up or down for a given district. Okay, number 1. Well, before we get here, the first method we'll study is Hamilton's method, which was approved by Congress for use in 1791, but was never actually used since President Washington vetoed the bill that introduced it. Hamilton's method. Assign each district a number of seats according to its lower quota. If this adds to the right number of seats, you're done. 2. If it does not, assign extra seats one by one to the districts in descending order of size of the fractional parts in the standard quota. For example, if 3 districts have standard quotas 2.93, 4.70, and 3.15, the first extra seat would go to the district with the fractional part 0.93, and the second extra seat will go to the district with fractional part 0.70. All right. It says use Hamilton's method to apportion the seats for the city described in the class portion of this lesson. In completing the table on the previous page, you've done most of the work already. Cool. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea ever. Okay, listen. I'm going to have to draw a table here. Now, let me put together a quick little table here. Hopefully I have enough room. All right, so I want to do the districts. 1, 2, 3. All right. So we will have the districts. Abbreviated. This is 1, 2, 3, 4, 5. And then we would go with our standard quota. Standard quota we already had was 2.67, 6.67, 3.42, 5.58, and then 1.67. Then we would do our lower quota. So this would be 2, 6, 3, 5, and 1. Now we would do our upper quota. So we have our upper quota, which would be 3, 7, 4, 6, and 2. Now, before we move on, we look here and we add up the lower quota first. 2 and 6 is 8, plus 3 is 11, plus 5 is 16, plus 1 is 17. So we notice here that the lower quota does not work. So what we have to do is the second part of Hamilton's method. We have to determine how many seats we're missing. We have 17 seats with the lower quota, so we're actually missing 3 seats because we want to get up to 20. So what we would do, we would go back to the standard quota and look only behind the decimal. And we would find the 3 largest values behind the decimal. And it just so happened that all 3 of them are the same. It'll be from District 1, District 2, and also District 5. It'll be the 6 sevens. So with those districts, I'm going to write seats here. So with those districts that we had the 3 highest values, which is 1, 2, and 5, you're going to use the upper quota from those districts. So District 1, you will use 3. District 2, you will use 7. Districts 3 and 4, you will continue to use their lower quota. And then District 5, you will use the upper quota as well. Now, when you do all of this, this should equal up to 20. 3 plus 7 is 10, plus 3 is 13, plus 5 is 18, plus 2 is 20. So this will be the amount of seats you would have. Now, we move on to the next page. It says here, the apportionment method that was adopted by Congress after Washington's veto in 1792 was designed by Thomas Jefferson, and shockingly is called Jefferson's method. It's a bit more complicated than Hamilton's method. It uses what we call a modified divisor. The idea is to make sure that every district gets its lower quota. We know that won't work in general because usually the number of seats will add up to something less than a correct total. In Jefferson's method, we'll make the quotas get bigger by making the standard divisor lower. Remember, the standard quota comes from dividing the district population by the standard divisor. So if the divisor gets smaller, the quota gets bigger. So now we look here at Jefferson's method. Number 1, it says assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. Number 2, if the sum of the lower quotas is less than the number of seats, choose a modified divisor that is less than the standard divisor and recalculate the lower quotas. Use this as the apportionment if the lower quotas now add up to the total number of seats. If not, adjust the modified divisor and try again. Okay, Jefferson's method ends up being a trial and error process. We keep trying different divisors until the lower quota add up to the right total. Let's give it a shot. Recall that the standard divisor calculated earlier was 12. Now we know that 12 was really 12,000. Fill in the table below, in each case getting a modified quota from dividing a district's population by the modified divisor 11. So when it says dividing by 11, we're thinking 11,000. So what I'm going to do here, I'm going to write it out at the bottom. Give myself enough room. So this would be District 1, it'll be 32,000 divided by 11,000. District 2 would be 80,000 divided by 11,000. District 3 would be 41,000 divided by 11,000. District 4 would be 67,000 divided by 11,000. And then finally, District 5 would be 20,000 divided by 11,000. Now, we will go to Desmos. Let me see something here. Okay. Yeah. All right. Now, what we could do here, we could just change these denominators. That's what I like about Desmos. We don't have to reinvent the wheel. All right. So now, 32,000 divided by 11,000, that'll be 2.91. 80,000 divided by 11,000 would be 7.27. Then this will be 3.73, 6.09, and finally 1.82. So now we have all of these values. So we will put in our modified quota. This would be 2.91, 7.27, 3.73, 6.09, and 1.82. So the modified lower quota, remember, we just take the digit that's in front of the decimal. So this would be 2, 7, 3, 6, and 1. Now it says add up the modified lower quota. Does this apportionment work? So we add 2 plus 7 plus 3 plus 6 plus 1. And when we add that up, that gives us 19. And it's no, still 1 seat short. All right. So now that we know we're 1 seat short, that means that our divisor has to get even lower. So we will go here to number 4. Now with number 4, it says our next attempt would be to change the divisor we're using. Do you think we should make it bigger or smaller? And the answer would be smaller. And that is because we still need an additional seat. Okay, number 5, it says try again with modified divisor 10.5. Now 10.5 is actually 10,500. And then they ask us, does the apportionment work now? Is it the same as the one we got from Hamilton's method? So what we're going to do here, we're just going to make this 10,500 for the denominator. Now, if you want to write that out, that's fine. I'm just going to put it in the Desmos calculator. Then we could go back. So the modified quota would be 3.05 for District 1. District 2 would be 7.62. District 3 would be 3.90. District 4 would be 6.38. And finally, District 5 would be 1.90. Now, we would do the modified lower quota. This would be 3, 7, 3, 6, and 1. Now, when we add these up, 3 plus 7 plus 3 plus 6 plus 1, it does give us 20. And then it says, is it the same as the one? Okay, does this apportionment work? We would say yes. And then they ask, is it the same as the one we got from Hamilton's method? Hamilton's method has different values for 2 of the districts. Okay, Jefferson's method was used in Congress until 1842, when it was replaced with the new method devised by Daniel Webster, a distinguished congressman, senator, and 2-time Secretary of State. Webster's method also uses modified divisors, but is based on standard rules around them rather than the lower quota. Okay, Webster's method. It says here, assign each district the number of seats by using standard rounded rules on the standard quota. Rounding up if the fractional part is 0.5 or greater, and down if the fractional part is less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. If there are too many seats assigned, use a larger divisor. If there are too few seats assigned, use a smaller one. Okay, now we come here to the back. It says we already know from question 7 in the class portion that using standard rounded rules won't work for the apportionment problem we've been studying. That resulted in 21 seats. So we can skip right to step 2 in Webster's method. Since we have too many seats, we should try a larger divisor. It says here using a modified divisor of 12.5. Now we know 12.5 is the same thing as saying 12,500. So basically, we'll take all these values and divide them by 12,500. So we just change a few things here so we don't have to reinvent the wheel. All right. So we look here, our modified quota for District 1 will be 2.56. District 2, it'll be 6.40. District 3, it'll be 3.28. District 4, it'll be 5.36. And District 5, it'll be 1.60. All right, now, if all went well, you will find that the number of seats is too low. Oh, we need to do the modified rounded quota. So we need to do regular rounding here. This around a 3, it's around a 6. This would be 3, 5, and also 2. because we know if the decimal has 0.5 or higher, we'll round up to the next whole number. If it has less than 0.5, then we would just keep the number in front of the decimal. All right. So when we add all these together, it just gives you 19. So if you add them all together, it just gives you 19. So we're still 1 seat short. So that means that what we were dividing by was too high, so we need to go down a little bit. So since we did 12.5, it seems as though this value is in between 12 and 12.5. So let's try 12.25. So 12.25 would be 12,250. So we'll divide each one of these by 12,250. All right. Now we divided each one of these by 12,250. Now I do need to draw a table here. For some reason, this pack is really stingy with the tables. So we add a district. We have, I guess if we did it like this, we'll put the population next. We had a district, we had a population, we had a modified quota, and we had a modified MRQ, which is a modified rounded quota. So we'll do District 1, District 2, District 3, District 4, and finally District 5. Okay, so this would be 32. Now we know this is in thousands. So we will have 2.61 for District 1, which would be the modified quota. District 2 would be 6.53. District 3, 3.35. District 4, 5.47. Then finally, District 5 will be 1.63. Now we do regular rounding. This would be 3, 7, 3, 5, and 2. So 3 plus 7 is 10, plus 3 is 13, plus 5 is 18, plus 2 is 20. So this works. So we could say it works. Okay, now we just finished page 103. Now we move on to page 104. Now I believe, if I'm not mistaken, I believe this is the last page from this exercise. So now, and we actually don't need the Desmos calculator for this portion. Okay, it says at this point you might be wondering, what's the big deal? Why so many different methods? Don't they all result in pretty much the same apportionment? Keep in mind that we're working with an example that has 5 districts and 20 seats to be divided up. For congressional apportionment, there are 50 districts, which are states, and 435 seats. In that case, different methods can result in significant differences. Another interesting note, an apportionment problem of that size requires a tremendous amount of calculation. So it's no surprise that computers are used. But think back to, say, 1842. At the time, there were 26 states and 242 seats, and the apportionments were done with no help on the calculations whatsoever. Those guys were pretty smart. In the technology portion of the portfolio, You'll do a little research on the history of congressional apportionment, filling in some of the gaps that we haven't mentioned within this lesson. In the applications portion, you'll learn about the method that's been in use since 1941, the Huntington-Hill method. Some of the examples below are apportionment questions, and some aren't. In questions 8 through 11, write whether each one is or is not an apportionment problem, and of course, justify your answer. Okay, number 8. A school district raises an extra $1.2 million when a levy passes and decides to divide it among all of the schools in the system based on enrollment. Okay, this would be not apportionment. And that's because a dollar can be divided up. Number 9, a manufacturing company with 4 locations buys 22 new stamping machines. The plan is to divide them among the locations based on production levels over the last 4 years. This is apportionment. Because a stamping machine cannot be divided up. Okay, number 10, it says each day a team of engineers that works for a utility company decides how to allocate power on the grid to various neighborhoods based on past usage statistics. This is not apportionment. Because power can be divided up. And last but not least, it says each day the manager of a large roofing company decides how to allocate workers to that day's job based on the size of the job and the time of completion. This is apportionment. And that is because a worker cannot be divided. And we are done.